Right. That was a lot of great content to follow. And I think I am gonna take it all the way back down to raw plumbing. Um, you'll see soon. So how many engineers in the structural engineers in the room? Just Toby and me? Three? Okay. So I suspect that a decent amount of everyone else thinks that structural engineering means you put in your structural model, you hit play, and the answer comes back out, and everything's fine. Life goes on. What's taking so long? So what I'll do in the next 15, 18 minutes here is give you a little bit of my personal perspective of my journey with this. I've worked at multiple firms at this point already, so obviously a lot of it is my personal experience. Come bring that to you today. So I'm my name's Kermin, by the way. So I'm an associate principal with ARUP, a structural engineer. I'm based in Chicago right now, but I've had the fortune of working, starting my career with ARUP in Los Angeles. And 20 years ago, I actually started my career at SOM, and like everybody else, and returned back to Chicago. So when I started SOM, Burge was 2004. Burge was going on, right? So that's my first project that I worked on. And then after that, we worked on the Trump Tower. So from the get-go, I had an experience, I guess, with pretty large projects. And as a result, that kind of like shapes where your career goes sometimes and what you get interested in. And here are a couple other images that I'll show that I've been involved with since then. So 2010, I think Anthony and I met. We were doing a lot of competition work. And this is the One Dubai Tower complex development, I guess. Like I just cropped it from your website yesterday. So this was in 2010. And on the right-hand side, you can see that our structural diagrams were so convincing that it turns out, I think Adrian or Gordon put it on CNN on the article. So I think we're probably the only ones that have our structural diagrams up on CNN. So that's a pretty nice thing. But more specifically, that was done all in 2010, right? It's 2024 now. Like, what have I done in the last 14 years? And that's a very scary question to ask in the last couple of days when I was pulling these images together. So my journey, right? What have we been up to since 2010? Like we did that tower. I mean, just for context, the tallest one is 1 kilometer, so that's big, right? So what have you done since then? So after 2010 era, like I moved to Singapore. I was working at another firm for a while. And these are 3 projects I worked on there. On the left, your left, will be South Beach Towers. It's a Forces and Partners project. You can see that's 2 office towers. Sloping columns, of course, no floor plates are the same. So geometrically and structurally complex there. In the middle is a 340-meter tower right next to Petronas. It's pretty slender, as you can kind of tell from the isometric. So did that tower as well. And then on right-hand side, Singapore Sports Hub, so obviously a big dome stadium with a movable roof. So what was complicated about all this stuff? So coming out of the One Dubai boom time, right? I moved to Singapore and I was working on this project. So on the left, I'm not going to get into excessive detail here, but like the structural models got more and more complex. No floor plates are the same. The columns are sloping. The uses are different. So addressing the fundamental structural stability of that was pretty challenging. And then on the right-hand side, as you might infer, from that simplistic looking dome structure, there's a lot of joints which are not the same. So everything's fun and games when you have your centerline model, your Y sticks all node out, hooray. And then you find out 3 years later, when they're fabricating, you got some nodes that have 11 elements coming in together, which is incredibly congested. And we're asking them to do these CJP welds. So that's when I think for my journey, we really started to kick in like the entire life cycle of, structural analysis, geometry, result management, and kind of like extreme automation there. So that's the right-hand side. So after this couple of projects, I wanted to move back to the US. So I joined Arup in Los Angeles in 2014. And we were very fortunate, I guess, that in the last decade, we've had the ability to use project after project to kind of push our technology boundary. So real quick, starting on the upper left, 2014, this is a Loma Linda hospital. Obviously a critical facility located 1 mile, I think, from a major fault. So extremely high seismic loads, both horizontally and vertically. The middle is Rapper Tower. Some of you might have seen it in some architectural other publications. That is not a rendering. So that's rail, no straight columns, no interior columns, but everything's kind of curvy. And then 2016, 2017, we won the contract to do the Legion Stadium. And this was done in 14 months from the day that they were initiated. So I think that is and probably still, right, the fastest design to construction to hand over a stadium, probably in the US. Funny story about that is that we were based in Los Angeles. We would fly out to Kansas. We would fly over the SoFi Stadium, and they already had steel going up. And you know who finished first. So after that, that was all a warm up. 2018, we were working on a very large museum project in Abu Dhabi. It's obviously not an ice cream cone, but if you Google Abu Dhabi Museum, probably see what I'm talking about. It's a Gary job, right? Nothing is straight there. A lot of curved surfaces. And then 2020 Cable Stay Bridge. That's basically a big structural analysis problem. And then 2021, we had a couple of towers in Beverly Hills. So starting the most complicated side of this, so performance-based seismic design. Arup has a history of advanced analysis. I think anyone who's interacted with Arup kind of knows this already. What that means is that we have in-house a lot of simulation capabilities, both from CFD perspective and material perspective, right? So we write ability to write our own material models, so we can model how isolators work. We can model how beams hinge. And that goes into a piece of software called LS-DYNA that is pretty much used for car simulations or drop testing. So we've taken, technology from outside the traditional AAC world and then kind of like bring that into our world to kind of improve our seismic performance-based seismic design. So this was a 2014, and then I think just looking back at some of the timelines of where technology was rolled out, I think Grasshopper was kind of like big in 2008. Sounds about right. AWS was launched in 2006. So this is not that far, from 2014. And then in 2012, 2013, a lot of H cloud wrappers started to appear, which means like there's companies are providing, simulation as a service, right? They wrap AWS for you, you give them your model, they run it for you, and then they take care of all the complexity. So this is what we have right now, basically, to support all that performance-based seismic design. So obviously a bit of a cartoon element, but start with the upper left, you have your stick structural engineer. They cook some spaghetti, right? They make an LS-DYNA model, and usually we run it through a lot of ground motions. So we have, ground motions of different magnitude, ground motions of different frequency characteristics. So there's a lot of simulation going on. Each of these models may take about 8 hours to run, so they run overnight. And so that's why we needed to have a cloud provider to, provide the infrastructure to run these simulations. So that's in the middle, Penguin Computing. And then over time, we built out a whole bunch of AWS infrastructure to kind of like process all that data. And then we close the loop by going back with some automated graphing and, Grasshopper stuff. Bottom right is basically just a cartoon showing that one analysis model run, right, might comprise 110 models because of the different ground conditions and things like that. And then you parallelize that further where you start pulling data out. So all of a sudden, right, this seemingly benign run your analysis model has now become a pretty serious HPC problem. So couple more images of base isolation. But so 2014 back to 2014. So this is when this project was really in high gear. I remember an email that I think one of our colleagues sent out before he went on paternity leave. He's like, I preemptively ran all 260 models because I'm going on paternity leave tomorrow. I'll see you guys in a month. Right. So we all of a sudden enabled this ability to pre-run a scenario that had not actually been discussed. Maybe it's a good byproduct, I'm not sure. But back then we just started with literally submitting these files to this HPC provider, and we literally would FedEx hard drives back and forth. So from LA, we put the hard drives into a FedEx box, send it to Utah, they copy the data, send it back to us, and then our IT guy would like plug it into the server. It would be dangling from the server rack because there's no shelf. And then we copy data. That would took like a whole week just to move data back and forth. And then we said, okay, who's got an unlimited internet plan at home that's significantly faster than what we have in the office? Okay, so you go take the hard drives home. So after 6 months of that, that got a little absurd after a while, and that's when we started moving to AWS. Just a couple of images of that project of, it's some serious seismic loads here. So you got all the seismic gizmos on this project. You got BRBs, you got isolators, you got dampers, moment for anything you can think of to basically seismically protect a building is probably on this project. Another shot of the base isolation plane and another shot of that. So it's pretty big steel here, right? And why does this matter is because bringing the nonlinear analysis up front, right, allows us to actually hone in on that structural efficiency because it suddenly really matters. You can throw a whole lot of structural tonnage at a problem, but without, I think, proper simulation, you don't actually know the performance you're getting. So after this, we said, okay, why don't we do a bigger hospital? This is a hospital in Turkey. This is a 1 million square meter base isolator hospital. So it's 10 million square feet, and it has 2,600 base isolators. And that was all simulated as one analysis model. Bottom right is just some graphs illustrating that, was significantly better than code performance, and thus, in a seismic event, you would have a lot less damage to your structure and especially non-structural elements, right, to keep the structure operational. Fast forward to 2016, this finally got completed, I think, a couple of years ago. Classic project, start, stop, but it finally actually got built. So this is not a rendering as far as I can tell. Clearly, you can see it's got curved perimeter elements. Those are structural. And there's no interior columns. Let's take a look inside. That's kind of one of the shots from the inside. You can kind of see like the band elements are flying, outside the facade. And we got complicated floor framing here. But specifically because this is based in LA, seismic loads are very high. So how do we make this architectural design, come to life in a plausible cost manner? So like all the hospitals that we've done, step one is to reduce the seismic loads as much as you can. So this one doesn't have as many gizmos, but it's got, a steel plate shear wall and base isolation. So once you get base isolate a structure, your loads obviously drop significantly, thus allowing you to design more efficiently. But the only way you can really quantify that is if you bring your analysis process up front to really explain to the client why it matters. Here's a shot of under construction. You can kind of see the structural elements on the perimeter. On the back side, you can kind of see the steel plate shear wall. So it's got green dots. Those are perforations, so you can kind of see that. And then you can kind of also see like a lot of in-plane bracing to basically hold the whole building together. So what's the point of bringing nonlinear analysis up front? So no numbers, no colors, left-hand side not isolated, right-hand side isolated, and basically it's a way to visually communicate what base isolation is and why you might want to be on the right-hand side and not the left-hand side. So this was in 2016, 17. So now the stadium's coming online. We won the project. And so now it's interesting. We take some infrastructure that we had built for something pretty complicated, and now we bring it back to the linear world. So back to the linear world. So Allegiant Stadium 2017. Yeah, it's got, cable truss in the middle. It's got a steel vessel structure, and then obviously it's got precast seating. And don't take it for me, like on the contractor's website, they justifiably claim, right, that this is the time duration in which they design and finish and deliver. But what's interesting from a computational design aspect, you might guess, right? The geometry is controlled by three colored surfaces: the cyan, the green, and the purple, and grids. So I guess four things. So this is when we basically started creating a process where we could define the whole roof geometry, you just using those three design surfaces. When I first started, working on this project, I was like, okay, I'm gonna create some project agnostic tools that are gonna draw trusses for any project I could think of in the future. And that didn't work out so well. So what ended up happening is create a whole bunch of project specific effectively throwaway tools. Unless they build that bare stadium, which is exactly a replica, then like we can bring this back. But other than that, these are throwaway tools that we created for the project. But these tools basically allow us to set out the whole geometry of the roof structure. So we set out the main grid, we set out the in-plane bracing, and specifically because we're doing this parametrically, we're also preemptively tagging all the connection types that are happening. And that's really important because after you generate this wireframe, it's very hard to go find conditions to address, in the CA/CD phase. So as much pre-tagging as you can, kind of helped us. I don't think we did it as much as we could have, but it was a good start in the right direction. We were contracted to deliver the steelwork in Tekla because the detailer wanted to adopt our models. So, but the concrete works was documented natively in Revit. So we had started creating a BIM database that we could go back and forth with native elements. So not just a representation, but natively writing, steel elements from Tekla into Revit, keeping as much meta information as we can, writing concrete elements from Revit to Tekla, so that we can obviously coordinate the structure. Simplistically, it's kind of represented by the cylinder in the middle. Basically, we have a custom database that we can check in our BIM, both Tekla and Revit, and then that allows us to version control. And more importantly as well, it allows us to track our quantities through time, because the project's going so fast, better hurry up. Right, so track our quantities through time. And as a result, we can do a bunch of LCAs as well because we have the BIM data. But it turns out that this was a little bit of a warm-up for what came next. So in 2018, the museum job came online, and coming out of the stadium, we had a lot of lessons learned, I think, scars, depending on your point of view. So in this situation, what we wanted to do is like really create or compact the whole structural geometry to BIM or to analysis in one go. Because as you imagine, it's an architecturally expressive project. So design surfaces were changing every other week. So, having that process as tight as we can allowed us to kind of like turn those things around as quickly as possible. So coming out of the stadium, basically this is some mega spaghetti here, but we send in the design surfaces on the left, and then we create both the BIM and the FEA at the same time. And that allows us to cross tag the elements, which is super important on a project with no straight elements or grids. So if you don't pre-tag, you have no idea where the beams are. On this project, we also started to do a lot of more front-end connection detailing, so to illustrate the conditions that actually exist. And on the right-hand side is one of the blowups of one of the steel connections, and you can kind of see why pre-tagging upfront is your friend, because it's very hard to find something after the fact. And then last slides here, a bit more simple. This is two towers in Beverly Hills. It's a Foster's job. Every floor plate is different, of course. So what do we want to do here, right? We want to make sure we catch all the cantilevers and identify for the design team, like, hey, where the slab's not working, you gotta pull that back in. We can try. So grabbing the designs, floor plates, surfaces from, the Revit, we are able to automate our floor slab analysis. So basically, we take all the floor slabs in one go, we structurally analyze them all in one go, we lay them out, and we identify just with pure colors where, deflections are too high. So you gotta pull that slab in. Purple means bad, pull that slab in. And lastly, just a couple of the explorations. Because we have a lot of nonlinear analysis ability in-house, we explore damping. We do that both obviously in the nonlinear domain. So that's the tower, going through a seismic ground motion. And what we were exploring here is, like, can we add additional damping to the structure so we lower flow accelerations, and then create less unrepairable damage, or create less damage to the primary structure. So we can do that with our nonlinear tools. And taking it back even more back to the really simple world, simpler world, right? This is a tower in Singapore, not very tall, 150-meter tower, but it's over a railroad track. Rail tracks, and it's got pretty slender core. So what you can see here is the primary scheme had a core wall, or has a core wall. It's got outrigger walls or outrigger trusses. It's got the perimeter columns that run down. And the bottom, you can kind of see those perimeter columns transfer because they need to go over the railroad tracks, right? So all of a sudden, you can kind of think like, well, what is the optimum solution to this, and how do I compare? Right. So your question is, like, for the same drift target, what if I only had core walls, right? How much concrete do I need if I want to hit the same drift target? What if I pull out some outrigger lines, less truss work? What if the transfer truss at the rail level was deeper, right? So how do we basically evaluate this in a timely manner, but also objectively, right? So you got to hold the drift targets, typically the constant. Coming out of the project that we compacted all our FEA on, we then had the ability to basically submit jobs to a web portal now. So we literally drag and drop our analysis models, and we run it all on the back end anymore. So as of right now, we have the ability to support 8 or 9 structural pieces of software. Structural engineers just drag and drop the models. It gets run in the background. We pull the data out, and then they're just doing the visualization. So we eliminate a lot of the manual data handling as much as we can. Right now, the system processes about 100 models a week, and we've been doing this for 6 years-ish now. So we got about 6,000 plus structural models on this thing that we started just to do a bunch of museum pieces. And it works at all scales. So back to where we started, that 1 kilometer tower, we wanted to hit a drift target, 1 meter, why not? And we hit it right on. And we make sure that we don't just do it at the big scale, right? We do it at the small scales too. So we kind of like do these ideas, we have a canopy system, like, hey, how big do we need to make these elements? Or a terrace system. So we've done this at multiple scales. So we don't want to give anyone the idea that it's just for the big stuff. Last slide here, coming all the way back to 2009, exploring some structural topology stuff. And with that, that's kind of like the last slide. And, thank you.